All right, good afternoon, class. Can everyone see the screen with the grades on it? Yes? Okay, good, thank you. So exam one has been graded. I want to make sure everybody knows how to access the exam, the graded exam. Is there anyone here that would be willing to share their screen and log in to Canvas as a student and show everyone like how you can see the graded exam that I've sent you? Is there anyone willing to do that?
I can do it.
You know how to do it?
Yeah.
You don't mind sharing your grade?
I don't mind sharing my grade.
Okay. All right. So I just want to make sure everyone knows how to do this. I'm going to make you a co-host.
Okay.
And I'm going to stop sharing my screen and you go ahead and share yours.
Canvas.
Perfect. All right. So yeah, right there on the side. Everyone see that on the side? How did you get there? Did you just go click on?
I went to, or I clicked on the recent feedback.
Go to your grades instead on that tab and see what happens there. You go to grades. If you click on that, yeah, exam one. What happens when you click on that?
It just takes me to.
Okay, there you go. All right, so that's it. And then if you click on that on the side, you'll see an attached file, and that will actually be, you can download the graded version of your exam, and you'll be able to see like where I took points off and things like that. Okay. So good, thank you.
Okay.
Let's see. All right, give me a second here. Okay. All right. Everyone see my screen again? Yes? Okay, all right. So the average grade in the class for this exam was about a 70. And then we had 9 A's, 1 B, 2 C's, 5 D's, 7 F's. And so here you can see the grade distribution. Highest grade was a 98, lowest grade was a 10. We have pretty much everything in between. So the number that I like to look at to kind of get a feel for where the class is, I like to look at this number here, which is the standard deviation. And so some of you know what standard deviation is, some of you don't, but I'll give you a real like basic idea of what standard deviation is. So let's say that there were only 2 students in a class. Okay, I had 2 students. And let's say that they both took an exam and one student got 100 and the other student got a 0. Then the class average would be those 2 numbers added up, divided by 2, that would be a 50. That'd be the class average. Okay, now let's say a different scenario. What if same 2 students took a test, one got a 75, the other one got a 25. Well, again, the class average, we'd add that up. We'd still get 50, right? Or maybe they both took the test and they both got 50s. And then add those up and the average would be a 50. So even though the average does tell you something, what it does not tell you is how far apart your students are from one another, the spread of the grades. And so you can see in like the first scenario, I've got one student who gets it and one student who doesn't. And then, you know, in this case, 50-50, they both kind of are at the same place, right? The standard deviation is a measurement of how far apart everyone is. And so this standard deviation would actually be 0. I mean, sorry, wrong. This standard deviation would be 0. And then the bigger the number is, the more spread out you are, okay? So the standard deviation for this class, for this test, was about 24 points. Now, on average, you know, I've been teaching for like 20 years. On average in a class, I see anywhere between, I think the lowest I've ever seen is like 11 for standard deviation. And the highest that I've ever seen is about 25, somewhere in there. So what this, and really, okay, so lowest is like, 11, 12, highest 25, but I normally, it's about 15, 16, somewhere in there. So I look at that number and I say to myself, we have a very, very large standard deviation for this class, which means we have a huge spread of students. And you can see it in the grades. We've got a lot of students that are doing fine. It seems like they understand the material, not a lot in between. And then we have a large group on this end that struggled with that exam. So whether that be test anxiety or whatever, it's just, I mean, at the end of the day, the grade is the grade. So, it's difficult to address, it's difficult to teach to a class that has a huge standard deviation, because on one end, you have to challenge the students who are up here. And on the other end, you can't, like, you don't want all these people to fail, right? But this is calculus, right? So the idea is that we'll have to prepare you for Cal 2. So it's not like I can slow down the train. The train has to keep moving. So look, it's the first exam. We have more exams. If you're on the tail end down here, it's not the end of the world. You have time to improve. Now, the thing is, what are you going to do different, right? So something has to change in the way that you're preparing, the way you're doing homework, whatever it is, something has to change. If you do the same thing and expect a different result, then that's going to be an issue, all right? In fact, some of you probably have heard that quote from Albert Einstein. You ever heard that? I don't know his quote, if it's his quote, but Albert Einstein, which you all know who that is, right? Said that insanity, the definition of insanity, is doing the same thing over and over and expecting a different result each time. So, moral of the story is, don't do the same thing that you did and expect that the next test you're going to get an 85 or a 90. You have to change something. So whether that means come to my office hours or schedule appointments with me, because I know sometimes my office hours, they don't work for you. You have my cell phone number. You can text me and say, hey, are you available today or tomorrow for a Zoom session? I'd be happy to do that. But do it consistently. Don't do it like 2 days before the test, or wait to get the review or something and then ask me questions. It should be happening throughout the semester. All right, any questions or comments or anything about the test?
I'm gonna send you one privately.
You sent me one privately? Okay. All right, so we are moving on, and I'm not going to go over the test at this moment. I'm going to give you time to review it. I'll probably at some point give everyone the answer key so you can kind of see exactly what went wrong, but I'd encourage you to take some time to try and figure that out on your own right now. You figure out, why did he take off? Because I don't mark a lot of detail as to what you got wrong. If you look at your graded test, it'll just say like, -6. And so I believe, were there 10 problems? There were 10 problems on this test, so each one was worth 10. So if it says like -2, it was something minor. And I probably just like circled it or something. But if it's minus like 7 or 8, that means there's like a fundamental gap there. There's something big that you're not seeing. All right. So just look at that and then see if you can't figure out the answers to those problems. Then I'll provide the key at some point, and then if you have more questions, we can go over that. Anything else?
Nope, just whatever I said.
Yep, I got you. All right, so one last thing I'll say about this is, when you look at a class average of 70, you start to wonder, like, is that good or bad, right? I mean, I already talked about the spread, the spread of students. That's not good, but is a class average of 70 a bad thing? And so you have to, at least I like to look at it this way. When you look at college, right? In the classes you take, you have those grades, right? I mean, those are the letter grades you can get at the end of the class. You can get A, B, C, D, or F. And so, what does a C mean, right? What does a C mean? Well, it just means that you're average, okay? That just means that you're average. Now, is it bad to be average? I don't know. I mean, there's an average, right? For everything, there's an average. So if you're average, you're average, right? If you're a B, then of course you're above average, right? And if you're an A, then, that's supposed to mean you're exceptional. You're above the average, right? That's what it's supposed to mean. And then D and F go the other way, right? Below average and then significantly below average. So if my class average is a 70, which is technically a C, then what we're saying is that the class average is average. Now, if it was a 75, that would be better, but it's not terrible to have a class average be average. But I would prefer we're all A's. I wish our average was up in the 90s, but it's the nature of the way things are. So, okay, that's all I'm going to say for that. I'm ready to move on if y'all are okay. No more questions. Okay.
Woo! Look at the math.
All right. So I know you were preparing for the test and you probably forgot what we were talking about. And I'll just quickly remind you that what we had ended with last time was I was giving you graphs of functions and asking you to tell me what the derivative looked like. Right. So we were saying, oh, over here, the derivative is negative. So we would have to have, a graph down here. And so that's what we were doing. That's where we ended. I'm not going to go and review all of that right now. I just want to kind of see if I can get your brain going again. But we were still in 2.2, which is talking about the derivative of a function. And there's still some things that we need to wrap up before we can move on. So as we've been talking about derivatives, we've had this new notation, right? Like if somebody gives you a function, f of x, and I want you to take the derivative of it, what I do is I write f prime of x, and that tells you, okay, I need to find the derivative. So I need to do the limit, right? And there's two different definitions I said that you could use, but there's all sorts of other ways that you could write the derivative or symbolize that you want to take the derivative. So if y is a function of x, okay, so y is some function of x, and I want you to take the derivative, I can write f prime of x, just like this. Or I can just write y prime. If I write y with a little prime, that means, hey, go take the derivative. If I write dy over dx, that also means take the derivative. And what it represents, and it's important for you to understand what this means, is this represents basically what is the change in y as x changes. That's why we use dy dx. dy stands for the infinitesimal change in y over the infinitesimal change in x. Look at it as slope. Remember, slope is rise over run, right? So dy is your change in y, that's a rise, divided by dx, which is your change in x, which is your run. So it's a way of saying, hey, we're trying to find the rise over run, but at a specific point instead of like a secant line, it's now a tangent. So that's just different notation. You could also write df over dx because this is the function f. So you could just write df dx. You could also write this d over dx. So this is basically telling you, hey, you're going to take the derivative and x is the independent variable. So x is the letter that's basically in your function. And what are you taking derivative of? You're taking derivative of this, which is that function. And then you have two other notations. Capital D with f of x, that would mean take the derivative, and capital D with a little subscript x, then f of x. All of those mean the exact same thing. So I know that's confusing and you're probably like, why do we have so many different notations, right? Well, let me explain to you why. The reason why we have these different sorts of ways to write the derivative is because calculus was created by two different men, right? Isaac Newton and Gottfried Leibniz, which I put his name here. And so when they were creating calculus, they decided, I mean, they were making it up, right? They didn't open up a book that had calculus in it. They were making up calculus So they just made up their own new notations and they used different notations. And so this notation is what Leibniz used, and Newton was using this along with this, all right? So now we have both of their notations. And there are pros and cons to both notations, all right? Sometimes the Leibniz notation makes a little more sense to use, and sometimes Newton's notation is a little easier to work with. You just need to be comfortable with both, all right? Any questions there? Okay, so Gottfried Leibniz, one of the co-founders of calculus. Now, let's talk about differentiable functions. So what is a differentiable function, right? A function f is said to be differentiable at some point if the derivative at that point exists. So remember, the derivative is a limit, right? Do I need to write it down? I can. The derivative of a function at a is the limit as x approaches a of f of x minus f of a over x minus a. And then the other definition was limit h approaches 0, f of a plus h minus f of a over h, right? Those were the two limit definitions that you had to choose from. So if a function, if this limit exists, because when we were studying limits, remember, when we take a limit, you can actually have a limit not exist, right? Remember, if you take a limit and it comes in from both sides and it doesn't go to the same place, then a limit doesn't exist. So it is possible to have a limit not exist. But as long as the limit does exist at that point, then we will say that the function is differentiable at a. So that's just new language for us. Now, this next part of this is just extending the idea that instead of talking about a function being differentiable at a point, a single point a, what if the function is differentiable at every point inside some interval? So instead of saying, hey, look, let's look at what's happening to this function at a and saying, is it differentiable? We say, okay, look at an interval. Okay, so like look at all the numbers in between here and here. We'll call it capital I for an interval. If the function happens to be differentiable at every point in that interval, then we will say it's differentiable on the interval I. So do you see there's a difference in the language? Differentiable at a point versus differentiable on an interval. Those are two different things. I would say differentiable on an interval. Interval is a little more, there's more there because you have all these points in the interval instead of just one. So it's a little harder to be differentiable on an interval than it is to be at a point. All right, next idea. Differentiability implies continuity. So when we were studying this chapter, when we started, we said, hey, we're going to start to introduce this idea of a limit, right? And then from that, we established this thing called continuity. And we didn't spend a lot of time on it. But what continuity should mean to you at this point is that you can draw your function without picking up your pencil. So if you can draw a function, not pick up your pencil, you're looking at a continuous function. This theorem says that if you're differentiable at a point, then you must be continuous at that point. Okay, so automatically, if I know that I can go to some point A, if I know that the derivative there exists, then what I can guarantee you is that at this point we are continuous. So there's no holes, there's no breaks. Our function comes together nice. There's no gaps. All right. So differentiability implies continuity. Now, students mess this up, okay? Because, and this is not your fault, it's because most of you have not taken a logic course. So I want to talk quickly about the dangers of this theorem and how you can misuse it. So I'm going to write something down here on the side and let's just discuss this. Do you agree with this? If you live in Texas, okay, so I think we're all in Texas right now. So if you're physically in Texas right now, then do you agree that you are in the United States of America? Is that true? If you're in Texas, at least, I mean, Texas has not like seceded from the Union yet. So, you know, for now, Texas is still part of the United States, yes?
Yes,
And
correct.
that's a true statement.
Yeah.
If
Mhm.
Texas, so we
Yes,
can
sir.
read this direction. If you're in Texas, then you're in the US. Now, can you reverse it and it still be true? If you're
No.
in the US, then you're in Texas. No, right? You cannot do that. If you're in the United States, that does not mean you're in Texas. Not necessarily. Could you be? Yes, but it doesn't guarantee it, right? You could be in New York or California, but I'm not sure why you'd want to be there, but there you go. This is not true, okay? That is not true. Do you all agree?
Correct.
So this theorem, you have to read it the same way. It says if you're differentiable at a point, then you must be continuous at the point. It does not say that if you're continuous at a point, you must be differentiable. It is possible to have a continuous function and at some point, and then it not be differentiable. And I'll show you an example. So you just got to make sure you get this correct, right? Because math is very important about not only the language, but the order in which we state things. All right. So the question naturally arrives, when do functions fail to be differentiable? Okay, so when would you have a function that you cannot take the derivative? At some point. And there are three major categories of places where a function is fails to be differentiable. It's going to be either at a corner or a cusp. I'm going to show you pictures of all of these. Or it can happen anytime there's a jump in the graph. Or it can happen if we have a vertical tangent line. So let me show you each one of these. Here's the first one. Okay. So I want us to look at this. This is a function. Do you all agree that this is continuous?
Yes.
I can draw it without picking up my pencil, right? Okay. But just because it's continuous doesn't mean that at every point it's differentiable. I want you to focus your attention at what's happening at 0. If we go up to that point, we have a sharp corner, don't we? We have a very sharp corner there. And so let's look at what the derivative is doing. And this will test how much you remember of what we did in the last class. If I were to start coming here and picking points over here and ask you for the derivative, you would say, okay, I need the slope of the tangent line. And that would be a little positive slope there, a little positive slope there. Do you all agree all the tangent lines would be pitched up a little bit, right? So
Yes.
positive the whole time? Yes?
As we're going up, yeah.
Yeah.
And then
And then-
wouldn't it be at the corner that it would be 0 since nothing's happening?
Well, that's the question, because as we move up, now I have a way I can animate this. As I move up, okay, as I move this point up, let me clear that other stuff out. Do y'all see the little green there? The green is the tangent line. So would you all agree right now, as I move from left to right, the derivative is always the same value? In fact, it's 1. I have the computer calculating it for me, okay? Y'all see that? The slope of that little green line is 1. And then I keep moving, and then I get, well, let me jump over and go to the other side real quick. What about on the other side? Look at the slope of the tangent lines over here. Aren't they always -1? See, it's pitched down. But what happens at that top point? See, it's the slope is -1, but when I get to the top, it's going to immediately have to flip over. Do y'all see how it has to like immediately change from +1 over to -1? It's like an immediate flipping of it from a positive to a negative number. It's not a gradual, slow event that's happening. Let me kind of illustrate it over here. If I had something that looked more like a parabola, I go up to this point. Then as I come in from the left, right, the slopes of these tangent lines are positive, aren't they? But do you see how they're gradually flattening out? See how they're like gradually flattening out until I get to the top of the hill? And then once I get to the top of the hill, the slope should be 0 because I'm flat. And then once I get to the other side, now my derivatives are negative, right? Negative slopes. So it was a slow gradual progression from positive numbers through 0 into negative numbers. Where here, it's a sharp change, right? It goes from +1, and then instantaneously it has to go to -1. And because of that, it makes the slope of the tangent line at 0 undefined right there. I can't do it. Can't do it. There we go. Okay, so it's undefined at that point. So anytime we have a corner, we will have discontinuity at that corner. Another example that I didn't put here is what's called a cusp. And a cusp looks like this. Okay, this function at this point right here would fail to be differentiable. And again, it's because as you come in from the left, the derivatives are positive, 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 and then instantaneously you have to flip over and become negative slopes. And anytime you have that rapid change in the derivative, you cannot have the derivative exist at that point. Make sense? Any questions?
Nope.
I think somebody in the class, and I don't recall who it was, you know how I asked you to give me some feedback on the test? Wanted me to encourage you to answer questions and stuff like that, which I think I thought I had done that. I'm calling on you, but please do ask questions if you have them, because this is your education, right? So it's up to you to, if you don't understand something, to help me help you understand it. All right, rather than just sitting there and saying, boy, I don't get any of this.
So I have a quick question about
I don't have any questions,
like
please. No questions. No questions. No, I'm kidding, Brian. Go ahead.
If we ever have, if the graph is like coming vertically down and then taking a sharp right, kind of like the first one.
Right.
Well, can you show us like a different version of the graph that's also undefined? Because I want to make sure it's like, how do I say this? Okay.
Well, this would not be defined either. I don't know if that's what you mean, but
Yeah, that's what I meant.
yeah, like this wouldn't work either because that's a corner. Now, the thing is, the slopes of the tangent lines along here are all the same, aren't they?
Mm-hmm.
And then once you get to this point, it's like an immediate switching to that. So you go from this immediately over to another derivative slope, but it's immediate. Anytime you have a curve there, so I could fix it by doing this. If I had something look like this, that would be okay because it's a gradual progression. These derivatives slowly start to turn over and flatten out. And so that's okay.
Okay, so as long as it has a corner like that, it's non-differentiable.
That's right. Exactly. If you have a corner anywhere, then it's not differentiable at that point. Just at that corner, it's differentiable everywhere else. It's just the corner point that we'd say it fails to be differentiable.
Okay, I understand completely now.
Okay, good. Anyone else?
Yes.
So you want it from,
Oh, go ahead.
go ahead.
Claire, go first. Dilpreet, you're up next.
Okay. So you want it from like negative to positive, right? When it's going over?
Switching. It
Corner,
doesn't
like the
have to be. It doesn't have to go from negative to positive. Look at this one right here that Brian suggested. Everything over here, you have positive slope, don't you? That's a positive. All the derivatives are positive. But when you get to here, all the derivatives are still positive, but it's the fact that they switch quickly. Like when I mean quickly, I mean instantaneously. As soon as you get to that corner,
So
you
it's
have
like
to go from
immediate.
tangent lines that go like that to this, and there's no
Okay, I see.
yeah.
Yeah.
So I can't say it has to go from positive to negative. It could go from positive to positive. You could also have this. I mean, that
So
would
you just want kind of like a sharp corner where.
any sharp corner. Yep.
Okay.
Feel free.
You already did, sir. That's what I was
Good.
gonna ask. We have two negative.
Look for corners, okay? Look for corners. Doesn't matter how they're situated. As long as you have a corner, it's going to fail to be differentiable there. Okay, but that's only one of three different things we could have, okay, right? Corners or cusps, we just looked at. Now jumps, okay, this is the easy one. If you ever have a jump in your graph, then you're going to not be differentiable there. So for this one, if we go to this value, whatever, I don't know if that's -1, but at this value, there's a hole there. This would fail to be differentiable at this point. Let's call it A. Okay, it would fail to be differentiable here because we actually have a jump, a break in the graph, right? Remember, differentiability forces continuity. So if this were differentiable at A, then it would have to be continuous there, but it's not continuous, right? So if you're not continuous, then there's no way you can be differentiable. Maybe I should do this. This is kind of interesting for those of you who might, well, there's computer science majors in here, I know. So computer science majors and math majors study different things until you get to like graduate school. In graduate school, mathematicians and computer scientists really do a lot of the same stuff, which is a lot of logic. So remember how I said, if you're from Texas, then you live in the US, but you cannot do it the other way around. If US, then Texas, that's not true, right? But you can flip it around, but you have to change something. Here's what you would have to do. Instead of saying, if you're in the US, you say, if you're not in the US, then you can conclude that you are not in Texas. That is true. So in logic, what we do is we call this statement up here an implication. So we're saying if P, then Q. Okay, if P is true, then Q is true. An equivalent statement to that is to say if not Q, then not P. So you can flip the order, but you have to negate both of the statements. They're logically equivalent statements. So if you use that same logic, then if we're saying if differentiable, then it must be continuous. This is true. Then the equivalent statement would be to say if not continuous, then not differentiable. Oops. And that's exactly what's happening here. At this point A, we are not continuous, right? We're not continuous. You have to pick up your pencil. And if you're not continuous, then you cannot be differentiable. All right, that's not important. That's just kind of an interesting little logic thing. Y'all like logic? Logic is weird.
Yes, it's fun. It's a whole little game. It's fantastic.
Danielle, have you heard my pink elephant logic thing?
No.
Okay, so this logic gets weird, everyone. Okay, logic gets strange. So I'm gonna make a statement. You tell me if this is a true statement or not. All right. And by the way, in our logic system, all statements must be true or false. Okay. When you make a statement, it has to be true or it has to be false. There is no third option. Right. That's called the law of the excluded middle. It's actually a name for it. We take it for granted. Things are true or false. So I'm going to make a statement. You tell me if it's true or false. Ready?
Okay.
All the pink elephants in my room have wings. Wings, they fly. Okay. All the pink elephants in my room have wings. So what do y'all think? You think that's true or false?
All of the pink elephants in your room have wings.
All the pink elephants in my room have wings.
Well, then since there's no pink elephants in your room, then it's true because you're technically not telling a lie because there's 0 pink elephants with wings.
You're on the right track. You're on the right track, Cody.
Just because there's like pink elephants in the room, like that doesn't necessarily mean they all have wings, or you said that they do all have wings, or like
no, they all have wings. Look, all of them do.
Okay.
All of them. So in our logic system, that statement would be true. And here's why. In order to prove that it's false, you would have to produce or show me a pink elephant in my room that doesn't have wings. And then you could say, oh no, they don't all have wings. There's one that doesn't. Okay, so that is a statement that we say is vacuously true because the assumption is false. The assumption is that all pink elephants in the room, right, that there's actually pink elephants in the room. So if you ever, in our logic system, if you ever start with a false presumption, your conclusion is always true. That's weird.
Right.
That's the way it is.
I have you're jogging my memory back from like when I did logic. So yeah, I have like a whole thing on it. So that's why I was like, ooh, maybe later you can talk to me about it, because I wanted to talk about that kind of stuff mathematically, but my professor was not a mathematics person.
Yeah.
But so that would be really fun.
All of everything we do in math is built off of the same logic structure that you would take in a logic class. Okay, so it's all the same. There's no other logic. We just have one logic that we use. And if you're a computer science major and you're a computer programmer, you have to understand logic. You have to understand how things work, right? Okay, I'm going off topic.
Okay,
We've looked at the two types so far, corners or cusps, and then jumps in the graph. All right, third and last one is a little weird. Vertical tangents. Anywhere where we have a vertical tangent line. So remember, lines have slopes, right? And if you have a slope that's positive, it's pitched up from left to right. If the slope is negative, it's pitched down from left to right. When I do that, does that look left to right to you on your screen? Does that look like it's pitched down? It doesn't, does it?
It looks pitched up.
I'm reversed, right? Because my camera's reversed.
Yep.
I wonder,
Perhaps.
I think I can flip my video. Let me see if this does it. So that's pitched up, yes? Does that look better now?
Not flip.
Now that's backwards?
No, it just didn't flip. It's the same.
Oh, it didn't
Yeah.
flip it?
Yeah, nothing happened.
Where are my videos?
Could
Okay.
use your other arm.
Maybe I can redo my video.
Eh.
Yeah, I didn't do anything. Who cares? You know that positive slope means up from left to right, and then negative means down, and 0 means flat, right? But what's the slope of a vertical line?
0,
No,
right?
0's
Vertical. Oh,
flat.
I don't know. That doesn't exist, right?
It's undefined. Okay.
Right, doesn't exist.
Vertical lines have undefined slopes. That's something from college algebra you have to remember, that the slope of a vertical line is undefined. So look at this function right here, and let's look at the tangent. Can you see the little green on there? You don't see the little green as the tangent?
Uh-huh.
And do you see right here, I'm having the computer calculate what the slope is. Right now it's a positive number, but watch what happens as I get closer to 0. Do you, oh shit, sorry. See how it's, 1.5? Let me get a little closer. See how this slope is starting to grow? So get closer to 0. You see how that line really wants to become vertical? Now my slope's up at 21. I'm going very slow towards it. Now it's at 30 something. Now it's already at 100. I'm gonna have to stop at some point. I have to stop here. Look at my slope is already at 718. But as I get closer and closer, it just keeps on trying to get vertical. Now, if you actually do get to 0, you have a problem. Now my computer gave up, okay? Look at this number, 9.68 times 10 to the 9th power. So that's 9, move that decimal point 9 places to the right. It's a huge number. So once you get to 0, it's vertical, right? Do you see that that's a vertical tangent line? And that means you have an undefined slope, but the derivative is the slope, right? That means the derivative is undefined. And so you can't have a derivative at a vertical tangent. Now, what happens once I get past 0? Well, once I get past 0, everything's okay again, right? Because now I'm just back to numbers. So we have an issue, we would have an issue here, right here at 0. We have a vertical tangent there, and therefore the derivative would not exist there. Any questions on that?
Okay, it doesn't have to necessarily be at 0, right? So it could be
Yeah,
like
it doesn't have to be at 0.
to get 0. Yeah. Okay, just making sure. It don't have to be
I
at
could
0. It
have
could be like
something
37.
I could have something that goes like this, and that may be happening out here at 4. Okay, so it goes and it turns and it tries to get vertical, and then it turns back. So it'd be right here at 4, we have vertical tangent.
Would
Right.
the inverse of that work?
Would the what?
Inverse?
Would the inverse of that function have a slope? Is that what you're saying?
Would it have a differentiability?
It would have a differentiability. So if you were to graph the inverse of this, if it has an inverse, it would look like a reflection of itself. Oh, not doing good here, not doing good. Okay, that's kind of what it would look like. So it wouldn't be at 4 over here. It would be somewhere else. But that right there would have a derivative of 0 because the tangent line would be flat instead of vertical. I think that's what you're asking. If we looked at the inverse, then yes, it would be okay. Okay, so that's it. Those are the three places, the three things that cause a function to be fail to be differentiable, either a corner or cusp, a jump or break in the graph, or a vertical tangent. That's it. Those are the only three places we can have problems with differentiability. Now, this led, what I'm about to talk about here is a little off topic, but I think it's interesting because for a long time, mathematicians were wondering, hey, we can draw a function that, let me draw a function that looks like this. Is that function continuous? Is this a continuous function? Can I draw it without picking up?
Yes, technically, yes, it's a continuous function.
It's continuous, right? Now, there are problems. It fails to be differentiable in a couple of places. Fails to be differentiable here, 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 and here. Everywhere in blue, we can take the derivative, but all these little corners, we can't, right? So you would say here that this function, let's call it f, is differentiable everywhere except these points, 1, 2, 3, 4, 5, except for those 5 points, it's differentiable everywhere else. Agreed? Mathematicians asked, is there a function that is continuous everywhere, but nowhere differentiable? Meaning at every point on the graph, you can't take the derivative. You can still draw it without picking up your pencil, but you cannot take the derivative anywhere. That was the question.
Is it that one that goes up and down like that, like really fast?
Kind of. I'm not going to say up and down.
Like it oscillates like rapidly. I remember you kind of talked about that. It's like you said it in like physics math speak, so I don't remember.
Yeah, I mean, it does oscillate, but I don't want to confuse it with something we looked at earlier where it was like a sine function that started to oscillate a lot faster here towards 0. It's not that. Let me show it to you. Okay, so the mathematicians asked the question, does the function exist? Like, is there a function that you can draw without picking up your pencil, but nowhere can you take the derivative? And there is a function. It took a long time to find it, but it's called the Weierstrass function. And here's what it looks like. Okay, so what you can't see, it's really hard to graph this, but I'm going to have the computer try. So it looks like kind of like a sine curve from pre-cal, but there's an exception. If I zoom in on this, okay, so I'm going to zoom in. What you'll notice is that it looks like it's smooth, but what's really happening, and there's an easy way to explain this. What's happening is, it's better if I draw it actually. It's a function that does this, okay? So it's like saw teeth, like teeth on a saw blade, okay? But if you zoom in, what you can't see is that along this edge, there's saw teeth here too. And then if you zoom in on just one of those little saw teeth, like here's that sawtooth right there, just that one little piece, that thing has little saw teeth on it too. And then if you zoom in on one of those, each one of those has little saw teeth. So it's like this, you're trying to draw these saw teeth, but as you do it, you're like vibrating your hand and making little like infinitesimal saw teeth within each saw tooth. It would be impossible to draw by hand, but it would be continuous because you don't ever have to pick up your pencil. And at every point on the graph, there is a corner. It's crazy function, and it's not something you need to know. Like you don't need to know that like what it is, or we're not going to work with it. I just think it's an interesting idea. And maybe it'd be worth it if I actually show it to you.
Yeah, that's what I was trying to talk about. I didn't know what it was called.
It's a crazy function. Let's just go to Wikipedia, the trusted source of knowledge here. Here it is right here. It's hard to see this, but I'll just copy it here.
There's the equation. Yes.
Yeah, this is it right here. So that's it. And the thing is, you don't have any idea what this is because you haven't studied this yet. You study this in Cal 2. This is actually just a cosine function. However, it's not just one of them. it's an infinite number of cosine functions added together. So this sigma notation stands for addition. So what we're doing is we're adding up an infinite number of cosine functions together. And when you do that, you create this function called f of x, and it is the Weierstrass function, and it is continuous and nowhere differentiable. All right, I'm done. I got to move on.
Okay, then.
Okay, now that we know a little bit about, derivatives, and they fail to be differentiable sometimes, these three different places. Now we talk about something called higher order derivatives, which means, look, if you can start with a function f, right? And I can take, and I can tell you, hey, go take the derivative of it, right? You start with this function, you take its derivative, and you get a new function. Okay, you get a new function. But what's stopping us from taking derivative of that again? So doing the derivative a second time. Well, that's called a higher order derivative. And what we do is we put a double prime mark on that. So that means we've done the derivative 2 times. But there's nothing stopping us from going again. And we could have a third derivative, and a fourth derivative, and a fifth derivative, and a sixth. And so what we need to do is establish some notation for this. So here it is. F prime of x is the first derivative. We all kind of already knew that. Double prime means you're taking the original function, you're taking its derivative, and then you're taking the derivative a second time. And then the third derivative, 3 primes, means you do the second derivative, and then you take derivative one more time, which gives you a third. Now, if we keep doing this, it will start to become a pain in the ass to write like a bunch of prime marks, right? Like the 7th derivative, the 7th derivative, you wouldn't want to be all like 1, 2, 3, 4, 5, 6, 7, right? You wouldn't want to be doing that. So what we do instead is, instead of that, we just write in parentheses 7. And that lets everyone know we are talking about the 7th derivative of a function. Do not confuse that with this. That is not the 7th derivative of a function. That is, take the function and raise it to the 7th power. So that means take a function and multiply it times itself 7 times. This means take the derivative of a function 7 times in a row. All right? This is just notation. Right now, I'm not telling you yet. We're about to talk about why you would ever want to take this, the second derivative. Like, what is it useful for, right? We know the first derivative gives you the slope of the tangent line, right?
Mm-hmm. So is there an easier, faster way for me to get like the 7th derivative instead of taking it from the first one, the second one, the third one? That, like, you want me to do it over and over again?
Not in general. Not in general. I mean, if certain functions, you might be able to go fast to the 7th derivative, but in general, you have to just take each one successively.
Womp womp.
Now we have 2 notations, right? We have Newton's notation. This is Newton's notation, but we also have Leibniz. So how did Leibniz write second derivative, third derivative, fourth derivative? Well, remember that Leibniz used this dy over dx, right? And that's what represented the first derivative. Well, for the second derivative, he put a little 2 here in between the d and the y, and a little 2 on the x. And that's how he represented the second derivative. Notice that those are offset. Do y'all see how this 2 is over here in between and this one is over in the end, like on the edge? Here's why he did it that way, just so you know. He could have done this, but he was afraid that people would think that this means take the first derivative and square it. Because taking the first derivative, dy dx, and squaring it is not the same as taking the first derivative and then taking derivative a second time. So he didn't want this to be confusion. So he offset the 2's so that you wouldn't get messed up. And then third derivative, he did 3's here, and fourth, and then fifth. Does that make sense?
Makes sense, yeah.
Just notation. All right, now what can we use these higher order derivatives for? So higher order derivatives are important for a lot of things, but we're going to look at one specific example right now. Okay, so if we have a position function, okay, if you have some graph where, I'm going to try and squeeze it in here, where this x-axis is, let's call it t, is time. Okay, so this is time. And this axis gives you position. So maybe it's, you know, time is measured maybe in hours and the position is measured in like miles. Then whatever function you have in here, we'll call it f of t. We'll call that s. The book uses s, so I'm using s. So if we have s equals some function of time, and that gives us the linear displacement or position of an object. Okay, so it tells us where an object is at every point in time. Then the first derivative of that function will always give you the instantaneous velocity. This is a major deal, okay? If you know the position of something at every point in time, okay, that's what that graph would be. If you know where something is at every point in time, then you should be able to calculate the velocity at every point in time. And that's exactly what the first derivative gives you. It gives you a velocity function. Now, the second derivative gives you the acceleration, which would be this, a of t. Now, I always want to try and make this clear to my students because students can usually remember that the first derivative is velocity and the second derivative gives you acceleration. But I want you to look at it from a slightly different perspective. And I hope this doesn't confuse you. It's not meant to confuse you. It's trying to get you to understand this at a higher level. So if this is, let's say, time, and this is position, and we have a graph here, we'll call it f of t. Then if I go to some point here, A, and I ask you for the slope of the tangent line, right? I don't want it to be 0, but who cares, right? Then the derivative at A will give you rise over run, right? Isn't that what the derivative is? It's the slope of a tangent line. It's rise over run. Okay, so when we talk about rise over run, rise is our change in our y coordinate, right? It's our change in y. So that's going to be position. That's a position over the change in the x coordinate, which is a measurement of time. Position over time. So the derivative represents the ratio of position over time. So position might be measured in, let's say miles, and time might be measured in hours. And so your derivative is always going to have a unit of miles over hours. And isn't miles per hour speed? Right? Miles over hours is speed. So that's why this derivative gives you velocity. I'm going to call it velocity. Some of you who've taken physics know, maybe not, that velocity and speed are not the same thing. They're two different things because velocity is actually a vector, but we don't need to worry about that here. I'm going to say speed and velocity like they're the same thing, but later on they're not, okay? So we have to be a little careful with that. Okay. Are y'all okay with what I'm trying to get you to see? The big thing, let me illustrate it again. The big thing is, if you have a function and you take its derivative, the answer to the derivative or what it is will always be this over this. It'll always be the position divided by this, or whatever this is divided by this, okay? So now let's say we have a new function. And let's say this new function is this guy's derivative, okay? Which we said is the velocity. Now, the x-axis will still be time, but now this is velocity on this side. Or if you like, speed. So if I take the derivative of this at some point, it'll be rise over run. The answer should be the rise over run. So rise here is speed and run is time. So my answer should be speed over time. And do you all know what we call speed over time? I mean, think about, let me see, a speed would be like miles per hour. That would be speed, wouldn't it? And what if I divide that by time? So time would be maybe hours again.
Average?
Not average.
Average rate of change?
Nope.
Acceleration.
acceleration. So have y'all heard that the acceleration of gravity is 9.8 meters per second per second? Have y'all heard that
Yes.
before? Or per second squared? Have you ever wondered why they say per second squared? Have you ever wondered why they're saying per second per second? Well, it's because it's a speed divided by a time. But see, speed already has time in the denominator, right? Miles per hour is speed. And then you're dividing that by another speed. I mean, sorry, another time. So this is miles over hours divided by hours over 1. And if you flip the fraction over and get rid of it and multiply, then you're gonna get miles on top and hours squared on the bottom. And that's why your units for acceleration, this is what acceleration is. Your units for acceleration will always be some speed over some time, which turns out to be some distance over some time squared. So this is the same as distance over some time unit squared. Okay. Why am I showing you this? To confuse you, right? No, it's not to confuse you, all right? It's just to get you to understand that it doesn't matter what your graph is. If this is days, and this is, let me see, I'm just trying to think of something random. Days and
Elephant.
pink elephants, no.
Yeah.
Days and let's say COVID cases. COVID cases.
America's leading with the most.
Always lead. We always like to lead. So
To lead in the worst things.
if this function gives you the COVID cases, you know, relative to the days, we call this function f, then the derivative will give us what? This over this. This would give us the COVID per day. See, it's a rate of change. It's how much the COVID cases are changing per day. Understand? That's what the derivative would be.
So that's what I was doing in the hospital. When I was keeping track of everything, we would have to keep track of the amount of COVID patients we had, the day, and discharges and stuff like that. I had to calculate it.
Yeah, but you were probably doing average rates of change. So you were doing like a number at the beginning and at the end, and then you were finding an average, which would have been a secant line. What we're doing in calculus is we're looking at an instant in time and looking at the rate of change at that instant. And that would require a derivative. We can do all we can do average rates of change all day long and not need calculus. But averages are only good for certain things.
Got it. Okay.
Okay. So the main takeaway, everyone, again, the main takeaway is if you are given any function and you're asked to find its derivative, your answer will always be this over this, no matter what it is. It will always be that y-axis unit over the x-axis unit. That's what the derivative represents. Okay. Man, today is just me talking a lot. I apologize. We're not doing a lot of like math yet. It's just, sorry, I know it gets tedious here. All right, so I think now we are ready to move on to the next section. All right, I think we're ready. I'm not going to do any examples of this yet. We will in the next section. So here's the way calculus works. I mean, so this is like the time-honored thing that we always do in calculus. We always start out with the limit. Okay, from the limit, we talk about continuity. And then we talk about the derivative. Oops. Which we've done. And I've shown you that there are two ways to get the derivative, right? You have two choices. They both involve limits, right? Limit, limit, right? And we know that when you do these limits, life can suck, right? I mean, like the algebra here can be challenging. Would you all agree? If you've done your homework, if you tried it, you'll agree with me that this stuff can be hard. All the little things that happen. But what we do is in a calculus class, we actually spend a lot of time here and we make you suffer, okay? We make you suffer here with the limit definition of the derivative. And after you've suffered enough, then we tell you, hey, guess what? There's an easier way to find derivatives that doesn't involve the limit. It's just these basic shortcut rules that we're going to have. And so now you have graduated to now being able to talk about derivatives without having to do limits anymore, which is going to be good. But then you're going to be like, it's one of those things like, be careful what you wish for, because as soon as you start getting these rules, you start to realize that the functions you're asked to differentiate are going to get harder. So let me illustrate how this is going to work. Okay, so let's take an example. Let's let f of x be equal to x squared minus x. And I would like for us to find f prime of x. All right, so right now at this point in time, I've not given you any shortcut rules. That means I have to do it using the limit. And I have two choices on how to do it. I am going to make the choice to use that first or the second definition I gave you, which was the limit as h approaches 0 of f of a plus, or sorry, f of x plus h minus f of x over h. So that is, I'm using the second definition. That all look familiar to you? Okay, now what I'm going to do is start plugging some things in. I have to do limit h goes to 0. All right, so here we go. First thing, f of x plus h. That just means I take my original function f here, and everywhere I see an x, I'm actually going to put an x plus h in there. So I'm putting an x plus h here and an x plus h here. Let me do that. That's x plus h, and then I square it minus another x plus h. Is everybody clear that that is just that top left corner of this limit? There's there. Any questions? Now I subtract from that f of x. Well, f of x is just this function, right? It's just that function written out. But because it's subtracted, I have to put it in parentheses, right? That subtraction sign has to influence everything here. So I have to put that in parentheses to distribute, and then all of this over h. Any questions?
Yeah, I'm like ready for it to be over.
Ready to be over, yeah.
Yeah, I'm ready to go power roll. Come on.
I know.
Yeah, that's how I was going to ask how long before we go over the power rule so I can do this faster.
Yeah, I know. Okay, so now what I do is I have to expand x plus h squared. That means I have to multiply x plus h times x plus h. I'm not going to do it by hand. I'm just going to put what it should be. Okay, so I would trust that you could get that given enough time. That should be just this. And then I need to subtract x and h, so I need to subtract x and h. And then I need to subtract x squared, and I need to add x. So that's my entire numerator multiplied out. Now I notice that things cancel. X squared goes away, x squared goes away, x goes away, x goes away. And everything else that I have has an h in it. Once I know everything has an h in the numerator, I can factor an h out of the numerator. So I noticed that this has an h, that has actually two factors of h, and then this has an h. So I just pull an h from each one of those, and I'm left with this. And now I can cancel these h's. And at this point, now I no longer have division by 0 because that h is gone. So now I can take the limit. So I take the limit, I let h go to 0, 2x doesn't change. This h goes to 0, and I still have the minus 1 here. So my answer is 2x minus 1.
That was a lot right now.
Yeah, so that's what,
A lot.
coming into today, that's what we have to do to take a derivative, right? So now I'm going to show you something that I think you're going to be happy about. So let's go back up to this function here. I'm going to write it down here. This was the original function. And what I'm going to do is I'm going to ask you to look at this function and realize, first of all, that we have two terms, right? We have x squared and then we have minus x. So we have two terms, right? And each one of those terms is a power of x. So we have x squared and then this is x to the first power, right? So both of these are powers of x. So I want us to just do something, and don't ask why, let's just do it. What would happen if you take that 2 and you drop it down here and then replace the 2 with one less than 2? So take that 2 out here, and then instead of writing x squared, take 1 away. What's 2 minus 1? 1, right? 1, okay. And then you're done here. I want you to move to the next one, put the minus sign. I want you to do the same thing. So bring the 1 out front and then write x to what power?
0.
0, right? But remember, what is x to the 0? What's anything to the 0?
1.
1.
One.
So this is just 2x minus 1. Do you all see that? Because this is just 1. So that's 1 times 1. So do you see our answer here?
Yep.
Do you see that it's the same answer there?
Mm-hmm.
That is not a coincidence. That is where we're headed. Instead of having to do all this work, we're just going to start dropping powers down and subtracting. All right, that's what we're going to do. Let's do another example.
So why didn't we do this in the beginning?
Why? Well, here's why. The limit never goes away, okay? The limit never goes away. In Cal 2, there's the limit. In Cal 3, there's the limit. The limit is like, if you look at calculus, that's the heart, right, of calculus. All other branches of calculus come out of the limit. If you don't learn to use the limit in the limit definition of the derivative, then you can't really do anything else in calculus because you don't have that experience. Now, you all have heard of business calculus, right? The class, business calculus.
Yes.
So in business calculus, what they do is they do a little bit of the limit. They don't do any trig functions. They stay away from trig functions. They don't do any sine, cosine, any of that, okay? They strictly stay with just polynomials and stuff. And then they do a limit for just a little while, and then they go straight to the rules. They go straight to the shortcuts. So they don't really get the exposure that you get to the limit. And so if you try to go from business cal into like Cal 2, like a real Cal 2 class, you'll die because you don't have that limit foundation. And so it's just that you have to be able to do limits to do calculus.
Got it. Thank you.
Yep. And we're going to continue to do limits. They won't go away. So by no means am I saying the limit is gone. What I'm saying is that right now, to do derivatives, which is a certain type of limit, we will have shortcuts. Let's do a shortcut on this one. I'm going to give you a new function. X to the 4th plus x 3x squared minus 5x plus 1. All right, let's see if we can find the derivative using this little shortcut that, now I have not formally given you the shortcut. I have not like formally put it on paper yet, like what the rule is and how it works, the formula for it. I've just tried to get you to think through it. So let's start with this first one. We have 1, 2, 3, 4 terms, right? We're gonna look at them individually. On the first one, we have a power of 4 on x. So we're gonna drop it down. And let's see if people are paying attention today. Is Reagan here? No Reagan. Alberto? Jared? I think I'm gonna have to start removing some people here. David?
Can I tell you my answer?
No David. Caden? I think Caden's here. No Caden. All right. We're Damien. Am I in the right class? Oh shit, I'm in the right class. Where the hell is everybody? I thought I switched it over to your class. I apologize. All right. Vivian, how about Vivian? Nice job. Yes, Vivian, yes?
I'm here.
Okay, how you doing, Vivian?
Good.
Okay, were you following kind of what I've been doing or no?
Kind of.
Okay, so take this 4, drop it in front, right, like this, and then what power do you put up there on instead of 4?
3.
3, good. Yeah, all you're doing is subtracting 1 from the power. So the power comes out front, and then you subtract 1 from it. Good. All right, Vivian, I'm gonna stick with you.
Okay.
Do you see how you have 3 and then that's times x squared?
Yeah.
I want you to ignore the 3. We're just gonna put the 3 right here. And now I want you to do the same thing we just did on the x to the 4th on this one. So what do I do?
Is it gonna be x squared or just x?
Just x. What do you do with the 2? You have to do something with this 2 though.
Oh, do you
Just like we did.
multiply by 3?
Yep, we're gonna bring it out front. So it's gonna be multiplied times 3 and then it'll be x to the 1st power. That good?
Yes.
Okay. Gabriel, you want to pick up from where Vivian left off here?
Okay.
All right, so on the next one, I'll put the power on x for you. So can you tell me what the next piece will look like?
It would just be -5, wouldn't it?
-5, right. Because what happens? The 1 comes out in front. I'll write it down right here. We had a -5, and then the 1 came out in front. And then you subtracted 1 from x, right? And got 0. And that gave you x to the 0, which was 1. Is that the way you were thinking about it, Gabriel?
Yes, sir.
Okay. Good. Do you want to try the last one?
Does it just go away or?
It does. Now let's think about why, everyone. There is not an x there, is there? There's not an x. But you could, if you wanted to, imagine that there was, but it would have to be x to the 0, wouldn't it? And now do the same rule. So what comes out? 0 comes out, right? And what's going to happen when 0 comes out in front? It's going to kill everything off, isn't it? 0 times anything is 0. So basically that goes away. And you just get this expression, which I'll clean up. 4x cubed. I can do the 2 times 3, so I get plus 6x. I don't have to write the first power and then -5. Now, doesn't that seem a lot easier than the limit? Doesn't it? Okay, so we have a rule. Okay, you ready for the rule? This is it. This is the big deal here today. We have what's called the power rule. For differentiation. In other words, this is the rule we use whenever we have powers of x, whenever we're taking derivatives. So this is there. The thing is, in Cal 2, there's another power rule, but it's for integration instead of differentiation. So it's a different rule. So I just want to be clear that I'm talking about the power rule for differentiation. So here's what it says. It says if f of x is equal to x raised to some power n, then the derivative of that is just bring the n out front and then take x and raise it to the n minus 1. So you're going to just pop the n to the front and subtract 1 from the power. And that's your answer. And that's what we did on each one of these, right? The 4 came out, we made it x cubed. The 2 came out, we made it x. The 1 came out, we made it x to the 0. The 0 came out and killed everything off. Do you all see that that's the power rule for each one of those, one by one? Okay, so that is the power rule. Now I'm going to write it in another way. Here's another way we could write the same rule. If you have x to the n, and you take the derivative, remember that's what that prime means. The answer is n times x to the n minus 1. That's just a shorter way of writing the exact same thing I wrote up here. If you have something to a power, right, x to a power, and you want to take the derivative, bring the number out, subtract 1 from the power, and you're done. So I'm kind of in this position right now where I have to make a decision. Do I show you why this rule is what it is? And so I'm starting to think about those students who I need to challenge. Or do I move on and just let's use the rule? So I'm going to do a vote. I already know what I want to do, but I'm going to do a vote of the class, okay? And I just want to see, I know not everyone can vote, but I'm going to give you about 30 seconds to decide, do you want me to show you where this rule comes from? Or do you just want to, so yes or no means we're just going to take it on faith and we're just going to move on. 30 seconds.
That's the hardest I've ever thought today.
Me too.
Okay, I stopped the polling because it was overwhelming. It was overwhelming yes. So we're gonna go with yes, and I'm gonna show you. Okay. Now look, at a university, if you were taking University Cal 1, you would definitely be shown this. All right, because we just don't take things on faith. If we can show them, we show them. All right, but it's going to require a little bit of build up. Okay, so this is going to take up some class time, but I think the things that you're going to see here are going to be pretty interesting, hopefully. So before I can show you the proof of it and where it comes from, I have to establish a few things first. Okay, so I want us to look at what are called binomial expansions. All right, so a binomial is any expression that has two terms in it. So if we take the expression x plus y, that's a binomial. And what I'd like for us to consider is what would happen if you take that and you raise it to the 0 power. Well, anything to the 0 should be 1, right? So I'm going to put a 1 here and just follow this. You don't need to write all this down. You can if you want. Okay. It'll be on the video and I'll send you the notes later. I just more want you to understand what I'm doing. So does everyone agree that this thing to the 0 would be 1? Yes? Okay. Now,
Yes, sir.
what would x plus y to the first power be? Well, that would be itself, right? It's just x plus y. So I'm going to write that this way, x plus y. Don't ask me right now why I'm doing this, okay? You'll see why we need this in a minute. Okay, x plus y squared. That would mean I'm do it up here. I do x plus y times x plus y, and then I do x squared plus xy plus xy. So I'm foiling and I'm doing that, and then I put it all together, and here's what I would get. I would get x squared plus 2xy plus y squared. Yes, Danielle, I saw your chat.
Okay.
Okay. All right, so that's what we get, yes, if we did squared. Now, what if we did cubed? Well, then we would have to take that answer that we just got and then hit it again with x plus y. So I'm not going to go through the work on that. I'm just going to tell you what it is. It's x cubed plus 3x squared y plus 3xy squared plus y cubed. You just have to trust me that that's what it is, all right? And then what happens if we go again? X plus y to the 4th. Again, you're going to have to trust me. It's x to the 4th plus 4x cubed y plus 6, hold on, plus 6x squared y squared plus 4x y cubed plus y to the 4th. I'll do one more. If we do x plus y to the 5th, it'll be x to the 5th plus 5x to the 4th y plus 10x to the 3rd y squared plus 10x squared y cubed plus 5xy to the fourth plus y to the fifth. Now, do you think that I have all those memorized? I don't, okay? There's a pattern here, okay? And that's what we want to establish, is that there is a pattern in these. So I want you to pay attention to, let's just talk about the power of x. Just everyone look at the powers of x on each of these rows. On the first row, right, we don't have any x's, right? So we don't have any here. But on the second row, right, which is x to the first, this is to the first power, we start with an x, and then in the next term, the x is gone, right? It vanishes. On the next row, we start with x squared, which happens to be 2 here, and then the x goes to the first power, and then it vanishes. Here it's x cubed, then x squared, then x, and then it vanishes. X to the fourth, x cubed, x squared, x, and then it vanishes away. So what's happening to the powers of x as we move from left to right? Each step over.
Decreasing.
Just keeps decreasing by 1, right? And it always starts at whatever that power is. Y'all see that? X to the 1, x to the 1. All right, what about the powers on y? Do y'all see the pattern for the powers on y?
They increase.
It's opposite, right? It's like there's no y, now there is a y. There's no y, now there's y, now there's y squared. There's no y, there's y squared, there's y cubed. So it's the reverse of what the x's are doing. It starts from nothing and builds up, and it ends with that same number, right? Okay. Y'all with me still? So let's talk about the next row. I'm going to start writing it down. Here's what I can tell you it should be. I should have x to the sixth plus the next term is going to have some number here, then x to the fifth, and then there should be a y here. Plus now I'm going to have x to the fourth and then a y squared. So the x's are coming down, the y's are coming up. Plus some number in front, x to the third y cubed. Plus some number in front, x squared y to the fourth, plus some number in front, x y to the fifth, plus just a y to the sixth by itself. Do y'all see how I'm kind of using the logic of the pattern here? Now there's only one more thing for me to resolve, and that's what are these numbers, right? What are these coefficients here? And that, again, there's a pattern in this. All right, so I'm going to highlight the pattern. The pattern is this. Look at just all of the coefficients. We have a 1 here, a 1 here, and a 1 here. Here we have a 1, and then we have a 2, and then we have a 1. Then the next one is a 1, and then a 3, and then a 3, and then a 1. And then 1, 4, 6, 4, 1. Right, I can keep going. I'm going to now draw those. I'm going to draw these numbers without all the x's and y's. I'm going to do it up here. We have 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. And what we get here, that's just the coefficients written out. What we get is something called Pascal's triangle. Pascal was a mathematician, but Pascal was not the first person to ever discover this. The Chinese did it way, way, way before Pascal, but like a lot of things in history, sometimes people get credit for things they don't do. So anyway, he did work with it, but it wasn't his original idea. All right, so how does this thing work? The way it works is that the next row, you'll always have ones on the edges, okay? It's always ones here. And then this number, the next number that comes, like, do you see the numbers here? 2, 3, 4, 5. Do y'all see those? They come from adding up the two numbers above it. So like, well, you can say that for every number. Pick any number you want here, and it is just the sum of the two above it. Okay, so like this 10 is that 4 and that 6. This 10 is that 4 and that 6. This 5 is that 1 and that 4. And that works for every number on the triangle. That 3 is that 1 and that 2. That 3 is that 1 and that 2. That 2 is that 1 and that 1. See that? Two numbers above give you the one below. So can somebody tell me what this number should be then?
6.
6, right? Because it's this 1 here and this 5 added together to give you 6 here. How about this number?
15.
15. It's the 5 and the 10. How about this one?
20.
20.
20. It's the 10 and 10. Good. And then this one?
15.
15 again. Almost there. This one?
6.
5 and the 1 is 6. And there it is. Yeah? Okay, so now the big like final result of this. What if I asked you to consider x plus y to the nth power? All right. So I'm not telling you what the power is now. It's just some integer, positive integer. So what about the first term? What would the first term be? X to the n, right? That's always, because it's always like x to the 6, we start at 6. X to the 5, we have 5 here. X to the 4, we got 4. So that should be x to the n. Now plus, okay, now some number. Now the x power is going to come down, isn't it? So instead of it being n, it's now n what?
N minus 1.
Take away 1, but now we also have a y here, don't we? And then we have plus, and then we have another number in front, and then we have x. Now, how much have we taken away from the power this time?
All of it.
It was n, but now we've taken away not 1, but 2, right? So now it's n minus 2, and now y becomes y squared. So the power on y is coming up, power on x is going down. And do you agree that we would continue to do this? I'm going to say dot, 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 until we get to the very end. And what would the very last term be?
Y to the n.
Y to the n. Now there's a bunch of crap in here that we don't, I mean, we could keep writing out, but we don't know how long to go because we don't know what n is. So this dot, dot, dot means like it follows the same pattern the rest of the way. Now let's talk about the numbers. Let's talk about the numbers. Have y'all noticed that if you look at all of the second terms, these are all the second ones. Have y'all noticed that the number in front of the second term is always the power?
Yes.
Y'all notice that? It's always the power, isn't it? So for us, what should this number in front be? What's the power?
N.
N, right? So this should be n, shouldn't it? That should be n. Now the next number, I'm going to just concede and I'm going to say, I don't know, okay? To do what we're about to do, this is all I need. So does anybody disagree with this or have any questions about this? I'm saying that x plus y to the n should be x to the n plus n times x to the n minus 1 times y plus a bunch of crap that we don't know, and it will end at y to the n. We're all good with that? You understand where that came from? No questions? Good. Okay, y'all ready to prove the power rule now? Go. Prove that the derivative of x to the n is nx to the n minus 1. Here we go, deep breath. Okay, so I need to prove this, which means I need to look at the function f of x equals x to the n, and I need to find what the derivative of that is, right? I need to find this. But the only thing I'm allowed to use is the limit definition. So I'm going to write down f prime of x will be equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Everyone, that's just the definition of the derivative, isn't it? And that's the way we've defined. Now, there were two definitions. I'm using this one, okay? Now we just plug in. Okay, so let's do this. Limit h approaches 0. Now what we need to do is figure out this, which means we have to plug x plus h into this function right here. So I'm going to plug x plus h in here, which means I plug it in here. So Somebody tell me what this top left corner should look like. If you're plugging x plus h into that function.
X plus h.
X plus h
To the nth power.
raised to the nth power. X plus h to the n, right? That's what it would mean to take x plus h and plug it into that function. I replaced that x with x plus h, so I had x plus h to the n. Then I subtract from that what? F of x, right? Which is just what, Natalie?
X plus h.
What is just f of x?
F of x.
Which is
So x x to the n.
x to the n. So I put that here, right? And then all of that over h. So now what we have to do is we have to figure out what x plus h to the n is, right? We need to figure out what that is. Well, look what we just did. We just figured out what x plus y to the n is. So if I come in here and I replace all of the y's with h's, isn't that what we really want to know? X plus h to the n is this, right? Okay, so I'm going to just copy this real quick and take it over here. That's why we did all that work, just so I can do this step right here. I'm going to put it down here. Okay, there it is. So let's talk about that this thing right here. That should be according to this. Limit h approaches 0. It should be x to the n plus this part right here, which is n, x to the, let's see, n minus 1 times h plus some number I don't know, and then x to the n minus 2 times not y squared, but h squared, plus a bunch of crap we don't know, and then the very last thing will be h to the n. And we're not done on top. What do I still need on top? That's just, oh shit.
Minus x to the n.
Yeah, that's just this, right? All of that is just this. I still need to subtract from that x to the n, and then all of that over h. We're almost there. Do y'all see what happens in the numerator? You see what cancels?
X to the n.
X to the n minus x to the n goes away. And now the $1 million question. What can you tell me about every one of these terms in the numerator?
They all have an h.
They all have at least one h, right? How many h's does this term have?
Just one.
This one, right? How many does this one have?
2,
The next one would have
3.
then 4, then 5. And so we have an h in every single one of them, don't we? So let's factor an h out. If I take an h out of the top, I will pull an h out. And so I've removed an h from this one. So what am I left with if I remove h from here?
The n minus 1.
N times x to the n minus 1 plus some number I don't know. I will still have x to the n minus 2 here. And I have removed one of the h's from here, haven't I?
Yeah.
Which means I still have an h there. Plus dot, 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 all the way down to the end. Now I've removed one of these h's, haven't I? But just one. So that last one should be h to the n minus 1 because whatever the power was, I took one away. And then all of that over h. The h's cancel. And now it's time for the limit. It's time now to let h go to 0. And something, it's not miraculous, but it's awesome, is going to happen. Do you all agree that this has an h in it?
Mm.
So if h goes to 0, doesn't that go away?
Yes.
And doesn't every piece in here, all the little dot, dot, dots, don't each one of those have an h?
Yes.
And those are all going to go to 0, including the very last one. That one also has an h in it, so it goes away. And what's the only thing left?
The first number.
This, which is n times x to the n minus 1, which is the frickin' formula,
That is
right? That's the formula. We just proved that this is this, right? Every rule, so there's going to be a bunch of rules I give you. The first rule that you're getting is the power rule, okay? We're going to follow up the power rule with the product rule, the quotient rule, the chain rule. We're going to have all these rules. I don't think we have time for me to prove each one. It just takes too much time, right? This one took just too much time. But what I want you to do is from here on out, when I give you a rule, I want you to understand that there is some way to prove that rule. And it's, I mean, I'm thinking most of you followed me on this. I mean, would you have ever come up with that on your own? Probably not, but somebody figured it out, right? So we have to have an appreciation for these rules because they are very powerful and now we can use them, all right? Now I only have 4 minutes left, so let's do one more example, all right? Now we can use the rule, we've proven it. I'd like for us to take this function. I would like for us to find f prime of x. All right. So keep in mind, here's the only thing we know. If we have this x to a power, then the derivative of that, well, I'm just going to do it this way. This is all we know, all right? N x to the n minus 1. So when we look at this, do you all see that we could look at that as being x to a power? Isn't the square root really x to a power? It is, isn't it? Okay, so that's
Yes.
x to a power. This doesn't have x to a power, but I could imagine that there's an x to the 0 there. So that's x to a power, that's x to a power, that's x to a power, that's x to a power. Go ahead, Braxton.
Isn't square root x to the 1/2 power?
That is right. Yes.
Or is it-
This
Just
is
making sure.
x to the 1/2. Good. So do you all agree that we have x to a power for each one of these? Yes? And we know how to do the derivative of x to a power, right? But there's a problem, okay? There's a problem. The problem is that we have this big division bar here. And so the question becomes, can you just do the derivative of each one of these separately? Remember, when I first introduced this to you, I had us do this problem, right? And I told you there were 4 terms, right? I said there are 4 terms. And so what we're going to do is we're going to do each one individually and get our answer. And that was the correct answer. And that is right. But the reason why we were able to do each one individually is because they were separated by addition and subtraction. There was no multiplication between the terms and no division between the terms. If you have addition and subtraction, you can do them one by one. But if you have division like we do here, you are not allowed to do them one by one. And that sucks. However, what you can do is this. This is just algebra. We hopefully all know that if you have 3 terms in a numerator and 1 term in the denominator, you can split this into 3 separate fractions. You can do this over this, this over this, this over this. It's 3 separate fractions. Do y'all agree with that? It's an algebra thing. Now, each one of those you can simplify using properties of exponents. Remember, do you just subtract the exponents? So you just go like 3 minus 2 here, and you just get x to the first power. Minus, now this 4 is just going to come for the ride here. And then we have to do this, which means I have to take a half and subtract 2, which is the same as half minus, get a common denominator, 4 over 2. So that would be -3/2. Because you do 1 take away 4, that's -3, and then over the common denominator. So this is really x to the -3 halves. You all follow that? We're pretty much out of time, but I'm going to just finish this one last piece. This last one, again, if I have division there, I can't do the derivative. I have to have x to a power. So what I'm going to do is what they told you never to do in algebra, and that is I'm going to bring that back upstairs as a negative power. They always tell you in algebra, you can't leave your answer with a negative here. It's a bunch of bull crap. You can always have a negative there. There's nothing wrong with it. So I'm going to move that back up like this. Okay? Now, all of that was just algebra. At this point, though, now we have 3 terms. They're all separated by addition and subtraction, and every one of them is x to a power. So what I'd like for you to do is we're going to end class. Make sure you do all the homework from the previous section. All right, 2.1, make sure you've done all that, out of the schedule. Make sure you review your exam. And I want everyone to try this problem over the weekend. And then on what, Monday? Wait, no, wait, hold on. This is Tuesday. Sorry, my week, it's been a long week already. I'll see you on Thursday. I'm ready for the weekend, I guess. On Thursday, I'm going to ask everyone at the beginning of class to just hold up their answer to this to their camera so that I can just see that you've tried it. I want you to just do the power rule on each one of these. Use this rule for each one of those individually. All right? And then we'll continue next time with the rest, more rules and stuff. All right, everyone. Have a good one. Thanks for hanging out. I'll hang out for a minute if you have any questions.
Do you know when the next test is going to be? It's slotted for the 4th, but obviously